Welcome. I'm a professor in the physics department. I'd really like to welcome you to this Spring's Frontier of Physics lecture. In the great tradition of a public university, the Frontiers of Physics lecture series brings to the University of Washington and our state world-class scientists to explain to you the most exciting developments and discoveries in physics. The Frontiers of Physics was started in 2015 when Dr. Patrick O'Hara approached Professor David Kaplan with the vision of a public lecture series. We have so far showcased 17 outstanding presentations by top figures in the world, including 9 Nobel laureates. The topics cover a wide range of phenomena from the early universe to the present, from the extragalactic scales to the microscopic worlds and quantum mechanics. The lecture series is only possible by the work of a diverse and spirited committee with members of the faculty and our community who have joined with Dr. O'Hara and Professor Kaplan in realizing this public lecture series. So I'm very happy to welcome you here to Kane Hall. Many of you are part of the University of Washington community, including friends of the department and the College of Arts and Sciences. We also have guests from the broader community and some who've traveled quite far to join us. We have a special shout out to Mr. Gallagher's class from Port Angeles High School, which has made this a tradition, and we're so glad to have you back. And finally, thank you to all of you who couldn't make it in person and are joining us on the live stream. So I am very pleased to introduce Nobel laureate Dr. John Mather, who will be talking about the wonders of the James Webb Space Telescope. John won his Nobel Prize for extraordinarily precise measurements of the cosmic microwave background with the Kobe telescope. Some of you are probably own the t-shirt from XKCD with his measurements. But John's career has had multiple acts, and Kobe was but the first. After Kobe, John led the long development of the James Webb Space Telescope that is revolutionizing our understanding of the universe, first stars and galaxies, and revealing stellar nurseries in our own galaxy. For many of us, waiting and hoping for Webb's launch was a long and anxious undertaking. So many things had to go perfectly. And they did. The science has been stunning, and John will tell us all about it tonight. But of course, John is still innovating, and in conversations we had earlier today with students and faculty here at the University of Washington, he talked about his latest satellite designs for hybrid telescopes, where part of the instrument is in space and part of it is on the ground. It is this creativity and pushing the frontier, combined with his generous and kind mentorship, that makes John such a remarkable scientist. So following today's lecture, we will have our traditional Q&A with Dr. John Mather, where you can line up at the microphones on either side of the auditorium and ask questions. Please also remember to visit frontiers.uw, where you can sign up to our mailing list, view our past lectures, learn about upcoming events, and how to support the Department of Physics. So with no further ado, please join me in giving a warm welcome to Dr. John.
Tell you the story of the universe and how we found out out something today that I didn't know. So I'm going to tell you the story of this great telescope that you see on the screen. It's called the James Webb Space Telescope, named after the second administrator of NASA. He went up to Jack Kennedy with a plan for the Apollo program, and I'll show you this picture in a bit. Anyway, here is the great telescope as we imagine it to be in outer space. It's a great golden hexagon of a mirror. It's 6.5 meters across. Can we use metric units today? And then there's another non-metric unit, the sunshade, that 5-layer gray thing you see under the telescope is as big as a tennis court. So this thing was launched into space on Christmas morning in 2021, and it went up and has worked perfectly ever since. So we are really thrilled with that accomplishment. It took, as it says on the screen here, 20,000 people to make that happen. And there are about 10,000 professional astronomers in the world today, and we hope this is still working in another 20 years, so the ones that haven't even gotten to school yet will have a chance to use it too. So there it is. I am now no longer the senior project scientist. My successor was just named last couple weeks as received the Presidential Medal of Freedom, first astronomer to ever receive that. So these are all amazing team projects, and so when I was introduced with all these great accomplishments, I have to tell you, none of these things ever happen for a person alone. We do not go and sit in the crevice and think great thoughts. We work with many, many, many people, and I'll show you some of them. So there's the telescope, and I'll tell you more about it. But what are we doing this for? Well, questions that many of you have had, many of I have had since childhood. Where did we come from? And then, of course, what does actually we mean? Because it's not exactly sure where you draw the boundary. Does we mean draw a boundary around my body? That's not quite good enough, is it? Because my body has been changed over time. What's our cosmic history? That's the part the astronomers can work on. Where did the atoms come from? What did they do? Are we alone? Well, NASA's working on that. And where are the neighbors? We're working on that. So far, nothing, as you know. But people want to know, well, haven't we been visited by space aliens? Probably not. Sorry. We're probably the most alien thing that's ever arrived on this planet ourselves. But we think we know that story a little better than space aliens. So is life a miracle? Well, for generations, maybe thousands of years, people said, well, no, we don't know how that happened. It must have required a miracle. But these days, more astronomers, more scientists are saying, well, maybe it's always happens given a chance. So that would be the opposite. How far can we go? Well, not very far, darn it. People can get to Mars, and some people will go on a one-way trip, so they say. Elon Musk says he will go. But astronomers, we travel the universe at the speed of imagination. We take a picture, we draw you another picture, we make you a movie, and we tell you the story. So we travel as fast as you like, as far as you like. So other people can't do that, but we can. We can also travel back in time, because we look at things as they were when light was sent out to us, not as they are today. So how did we get here? Well, we got this long story we know about genetics. When I was about 6, my dad told me that people are made out of cells and we have chromosomes and they determine our future in some unknown way. It was even before the discovery of the double helix. So that gives you a clue that I was older. We do not have as much free will as people like to imagine. If you want to hear more about that, there's a lovely book by Robert Sapolsky, because actually what we are is human beings made out of roughly 30 trillion cells. They operate on their own. We've got about 86 billion neurons, something like 39 trillion microbes in our body. So when I say something that John Mather says, I'm speaking for what is nearly 100 trillion entities that make up my body. So that's a little tricky. Anyway, not going to go into much detail about that because you can't possibly. But anyway, now I'll tell you a little bit about my story. This is where I lived when my dad told me about chromosomes. He was a scientist working on the genetics of dairy cows. And so this farm was in far northern New Jersey, about a mile from the Appalachian Trail, and it was a real quiet place to grow up. So a place where you could learn science from a book, and where you could make things with hammers and nails in the shop. And so I learned science here from books a lot. And then I had the opportunity to go to college and all that stuff, and suddenly that passionate interest in astronomy and electronics paid off, and here I am. Who knew? So looking back in time, what happened in 1946? Here's Lyman Spitzer. He was an astronomer already. At the end of World War II, he wrote a little report that said, hey, people, we should build telescopes in outer space so we can do astronomy. And it's not just so we can look down on the Earth to do spy satellites, we should look up. So anyway, he said that, and we didn't do it right away, but it wasn't too long before we had the idea. Oops, what have I done? Oh, I can't see my own picture here, but anyway. So anyway, there he is. Lyman Spitzer told us to do it. There's 1950 about Sir Fred Hoyle gave the name of the Big Bang Theory to the idea of the expanding universe. He's confused the heck out of everybody ever since, because when you hear the name Big Bang, it's hard not to think of a firecracker going off at a place that already exists, in a space that already exists, at a time that already exists. But that's the exact opposite of what astronomers have seen. We see the entire universe expanding into itself. There's no boundary. There's no pre-existing space into which it pops. So that's Sir Fred. Thank you for confusing everybody. Calvin and Hobbes had a panel once when we tried to rename the Big Bang. He said it should be called the horrendous space kablooey. But that didn't stick either. I turned up in 1946. So what else happened? In 1948, these two guys, right and left, were thinking about the expanding universe, and we knew about neutron physics because we just fought a war, and we needed to know everything about that. And they said, well, okay, if the universe is expanding, it must have been hot when it was young. We should tell you how hot it is. And they got the right number about. They said it should be about 5 degrees Kelvin, 5 degrees above absolute zero. The right answer is 2.7, so pretty darn close. And nobody went to measure. If somebody had known there was a Nobel Prize waiting for them, maybe they would have tried harder. There was a Nobel Prize given for the discovery in 1965 by Penzias and Wilson at the Bell Telephone Labs. In 1948, it would have been actually a very hard measurement. But it was exciting enough that 300 people came to the PhD thesis defense of Ralph Alpher, who's the guy on the right there. So people knew it was important, but then they gave up for a while. So what else happened? And this is about 1954. My parents took me to the Museum of Natural History in New York City. I saw the planetarium show, and I thought, I want to know a lot about that. That is amazing, this whole story about the planets. And there's a gigantic meteorite, which is about as tall as from here at the top of the screen. You say, where did that rock come from? How did that fall on Earth? There's a story here. And by the way, there's no canals on Mars, even though there's canals on that map. We know, and this is a bit of a surprise, any idea how where those canals came from, since everybody saw them, but they're not there? They're probably the blood vessels in the back of the observer's eye. We fooled ourselves, didn't we? Anyway, then in '57, the Sputnik went up, and this country was completely petrified. Not that we didn't know it was going to happen, but it made it very clear that we could be attacked by nuclear weapons coming from space. Okay, we already knew about that. When I was a kid, we were taught to hide under the desk in case of nuclear attack. You sort of know that's not enough. Even if you're a kid, you know that's not enough. So anyway, so what did NASA do? NASA got created in 1958, the next year, and we said, okay, we're going to do something. We're going to prove that we can do stuff too. We can launch rockets, we can launch satellites. And then in '62, we'd already started the Apollo program. And here's Jack Kennedy. Let's see if I can play the audio. He's announcing that we're going to do this. And it's important to hear what he says as well as we're going to do this.
Some say the moon. Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
So notice what he said at the end, and the others too. He didn't say we're just going to do this and stop. He said we're going to keep on going and do the things the country needs us to do. So some of them are still not complete, but you can see that with the demonstration of the Apollo program and with the other things we've done at NASA, that if you get the agreement of the people to do something, we can do the most astonishingly complex things. So here is James Webb, the man who actually made that happen. And so in it was 7 years after that speech, we actually had astronauts landing on the moon. So, yeah, thank you. So now coming back to astronomy, where does this story come from that I'm telling you? Back in 1929, it was noticed from this graph prepared by Edwin Hubble that distant galaxies are going away from us with great speeds that are roughly proportional to distance. So if you run the movie back in your mind, you say, well, if you go back a certain amount of time, we were all together. And it looks like we're at the middle because everything is going away from us. And so each of those dots represents a single galaxy of about 100 billion stars, like the sun, held together by gravity. So that's the story of the expanding universe. It was noticed in 1929. It had actually been predicted in 1927 by Georges Lemaitre, who was a Catholic priest in Belgium, who also had a PhD from MIT, and he used Einstein's equations to predict that this should be true. Einstein heard that story and said, that's ridiculous. Einstein has been wrong, but he was right an awful lot of the time too. So anyway, 1929, we know the universe is expanding, and it's almost a century since we found that out. It's also almost a century since we found out about quantum mechanics, so we should be having lots of celebrations coming up real soon now about the discoveries and astonishing surprises of science. So what did we do about that? Well, I'm skipping over a lot of time. So it was predicted in 1948 that the cosmic heat should exist. In 1970, I was a graduate student in Berkeley looking for a thesis project, and we said, let's go measure that cosmic heat, which had just been detected. Okay, got a thesis out of it, but my thesis project didn't work. So in 1974, I got a job at NASA in New York City. NASA said, this year we want proposals for new satellite missions. It's only 5 years after the Apollo landing. What are we going to do now? We're done with the moon program almost. Boss, my thesis project failed. We should try it in outer space. So we did. We wrote a proposal, and we sent it to NASA. I thought that'll never work, but it eventually flew 15 years after the napkin sketch, and there it is in outer space as we imagine it to be. And it very quickly confirmed the expanding universe story. And then I'll show you the picture that comes after this. Not only is it the right story, but we got the details of it. So that's the observatory as it was. It's probably still up there, but we're not using it anymore. So it had instruments to measure the spectrum of the cosmic heat to see if it's the right brightness at every temperature, and to make a map of the sky. So we were using equipment that could see waves that have a wavelength of about 1 millimeter. So it's a lot longer than the waves you can see with your eye. And that tells us something about the very early universe. This is what we call a baby picture of the universe as it was when it was 400,000 years old. So in our story, the universe was opaque in the beginning, then it cleared up when it was at this particular time, 400,000 years, and the heat and light that were there then was able to travel in a straight line, more or less, to our detectors. So we're looking at a map of the entire sky with pink and blue blobs on it, which are, of course, artificial colors, to tell you that the timely variations of temperature are part in 100,000 from one part to another. Stephen Hawking saw this picture and he said that that was the most important scientific discovery of the century, if not of all time. So why would that be so important to him and to all of us? Well, number one, if those spots were not there, then we would not exist. These are the seeds that turned into the structure of the universe. The galaxies, the stars, the planets, and the people are here all because of those spots. So gravity was able to overcome the expansion and pull back material to form the first objects. So how did that happen? Well, that's a subject for more work, but anyway, it has been confirmed, and yeah, it was pretty important. So I got to show my graph at many places. I've probably shown it 1,000 times by now, and there I am getting my diploma from the King of Sweden in 2006. And boy, can they throw a party. The party lasts for about 10 days. And it's fun. So, oh my goodness, this slide is a little old because this Hubble is now 34 years old. The Hubble Space Telescope was launched in April of 1990. So it's now 34 years old, and it's working beautifully, although it is old, and it's people have been up to fix it and improve it 5 times, you know, so that's why it's working so well. So that was the number 2 thing to do. It was launched a few months after the Kobe satellite, and so of course now we're going to see if the story we're telling is true. So after they got it working and fixed the focus problem, the first thing they said was, well, that was great, we need another telescope that's even better. And they wrote a little book and they said, please build us one that does what the James Webb Telescope does. So here it is, another picture of it in outer space as we imagine it to be. We see that at the top it says a joint project of NASA with the European and Canadian space agencies. They've all chipped in to make this work. It has been constructed with one very large aerospace contractor, Northrop Grumman. Their headquarters is near LA Airport, so we spend a lot of time on airplanes going to visit them. We have 4 instruments on board that collect information to make pictures and spectra. So a picture, of course, is just an image of a piece of the sky, and a spectrum spreads out the light of a star into its different colors into a rainbow to see, well, what's in it, what are the chemicals that make it up, how fast is it going, how hot is it, and things like that you can tell from a spectrum. So for an astronomer, a spectrum is worth 1,000 pictures, and a picture is worth 1,000 words, so that's a lot of words that a spectrum is worth. And indeed, many millions have been published about spectra. So it was launched on Christmas morning of 2021, and when we launched it, we said, promised 5 years of operations. Now we're expecting 20. So here are people I want to thank for making this happen. These are my project managers that I worked with. When it was introduced that I was the scientific lead, I should say I'm not the project manager for any of these things. I'm a scientist, so I do not try to coordinate the work of 20,000 people. These people do that, and to me it's a miracle of modern life that anyone could possibly make that happen. So there they are. Bill Oakes was our final project manager at Goddard, and Scott Willoughby at Northrop Grumman. When you ask Bill Oakes, is it going to work? Of course he says yes. And I thought so too. But then there was a bit of a story we had to deal with. In 2011, we thought we know what to do, but we can't do it because we don't have enough money in the plan. So we told Senator McCulsey, and she was pretty annoyed with us. So she wrote us a letter and said, please figure this out. So we got review committees, and review committees said, okay, did great work, didn't ask for enough money. So that's a pretty good report. You see there, our head of NASA was Charlie Bolden at the time, Marine Corps general, as well as an astronaut, and they worked together to make sure that the money was found in the congressional budget process to make us able to do the right thing. So thank you to both of them. When I show you this telescope and its results, I should say it's a political an international miracle as well as a technical one. So just a little bit about the technology that it took. We had to invent 10 new ways to do things, and I'm not going to tell you any details about them, but we needed better detectors, we needed better electronics, we needed a refrigerator to cool something down to 7 degrees Kelvin. We needed a device called a micro shutter, which has 250,000 tiny shutters that can be opened or closed by command. And of course, we had to figure out how to unfold it in space and make it focus. So I'm going to show you our scary movie after this. Here's the launch, Christmas morning. It looks like it's dark, but it's actually because just the rocket engine is so bright. It was 9 o'clock in the morning there, and I watched it from the sofa in my house because it was COVID time and everybody who didn't have to be in the control center was at home. So this is where we sent it. This is the place called the Lagrange Point 2. It's 1,000,000 miles from Earth, and we orbit around that spot. It's a place where the telescope sees the sun, Earth, and the moon all in one direction. You can put up the big umbrella and get cold. Here is our scary movie. This is sort of like the 7 minutes of terror that we had for the Mars landings, but ours takes 2 weeks. And that's good, because if something goes wrong, we have time to interrupt it and send a new command. And we didn't have to do it. Everything worked so well, we actually got to do things a little sooner than expected, which was lovely. And there were about 344 single-point failures, we call them, things where if that doesn't work, the whole mission is a loss, and they all worked. So how is it possible that you can do that? Well, very carefully, short version. Long version is lots of rehearsals. We unfolded this thing 4 times in the laboratory. Another part is you get lots of your grouchiest friends to come and tell you if you're making a mistake. We call those review committees, and they're always painful and always valuable. So here the cables are pulling on the sun, 5 layers of the sunshade, separating them so the telescope will be really cold. The last part is to unfold the telescope itself, and this all happens in the first 2 weeks. You can't use the telescope yet, though, because it's not cold, and it needs to be cold, and it's not focused. So it took us all together 6 months to get it all set up and working. And there's another miracle. We rehearsed how that was going to happen, and we stuck to the schedule. How do you rehearse with a telescope that you don't have? You make a digital copy. You make a computer program that sends you the same answers as the real thing would send, so you can practice. So you practice, practice, and practice. So just for anybody here who has to go make a new project, there are a lot of things to think about when something is as risky and dangerous as this. We had a question of, well, Murphy's Law, things will go wrong. Well, we had one case where it went wrong after it was tested. That's hard, but we fixed it. We are not personally very good at risk management. At least 12 of my friends have fallen off of ladders. So I can do that, but I shouldn't. So we have a very formal risk management process because we have to manage ourselves. I can do that, doesn't mean I should. So we write things down, and we have a manager who has to say, if we didn't do it right, we are guaranteed to fail. So that's some of my aphorisms for next time. So coming back to the astronomy, we have built an infrared telescope, which means we pick up light that's got longer wavelengths than you can see. And so why do we do that? Here is an example of something that's really different when you compare the visible picture and the infrared picture. Here is a star surrounded by dust. And the dust is that luminous cloud that you're seeing, and you can barely notice that there's a star in the middle. If you take a picture with the infrared, you can see through the dust. So it's a quite dramatic demonstration that dust grains that are smaller in size than the wavelength of light that you're looking at sort of become transparent. Light's a wave. So that means that light can go around an obstacle and reassemble itself afterwards. That's what's happening with those dust grains. So now you can see that this is a star in the middle, and it's sending out jets of material from the north and south poles, and that's a whole other story. But I'm just showing you that infrared light lets you see stars that are being born, stars that are dying, either case. We want to see things that are too cool to emit their own visible light. You're sitting there emitting 500 watts of infrared power and you don't even feel it. But if you were in outer space, we could see you halfway across the solar system with this telescope, because it's extraordinarily powerful and it picks up light from things that are not warm enough to emit their own heat. This, by the way, is a picture of the debris around a star that is disintegrating. When stars get old, they die one way or another, and this one happens to be sending out puffs of its atmosphere into this complicated pattern, and the pattern is due to the fact that there are other stars nearby. So stars are born, stars die, and the stuff comes back out, and it gets to be recycled, by the way. You and I are made out of material that came from the insides of stars. Everyone has heard the phrase, "you are stardust." Well, it is literally true. Almost all the atoms you see in this building were formed inside stars by nuclear reactions, and then the stars got old and sent the material back out to be recycled. So no, the Big Bang gave us hydrogen and helium, nothing else. But they didn't get carbon, oxygen, nitrogen, phosphorus, iron, all the other things of life. They were formed inside stars, every single one. Third reason to study infrared light is that the universe is expanding. Distant galaxies are going away from us at immense speeds, and that means we receive infrared light that started out as shorter wavelengths. So we have to build an infrared telescope to pick up light that used to be visible or even ultraviolet. So this is just a schematic, a sketch to say that the universe expands, build an infrared telescope to look farther back in time. So what did we see? Well, here is our most famous data release, the one that President Biden showed on July 11th of 2022. And what astronomers love about this is it shows many things at once. It shows bright stars. Those are the ones with a spike sticking out of the image. It shows immensely massive bright galaxies, the big fuzzy things in the middle. And it shows lots and lots of very distant objects, much more fainter galaxies, that have been magnified by gravitational lenses. Einstein told us this could happen, that light would be bent around other objects because of his idea about relativity. And so he was right. If you study the images of things around this bright galaxy, some of them will be very distorted. You see a lot of arcs that seem to be almost centered on the big galaxy. These arcs are magnified images of much more distant galaxies that have been bent and magnified a lot. There are places where the magnification gets to be 10 or 100 or even 1,000 or more, and so this is an immensely powerful tool that we have. So we know where these lenses are, wherever these giant galaxies are, and so we've got a big catalog of places to look, to use Einstein's extra lenses for our telescope. So what have we found out that's surprising? Well, the first galaxies that grew from the Big Bang material, what were they like? We thought we knew. Actually, we thought we knew a lot of times in the past, but we were wrong a lot of times. So this time we predicted that they would be very interesting. We did not expect to see what we did see. The first galaxies that grew are too hot. There are too many of them, too bright, and we don't know how that happened. So maybe that's just because we didn't know what was going on. So there are a lot of ways to try to imagine what you're going to see. And you have to do it a little bit to know you should build a telescope to see it. But here we are showing that that was a big science surprise. They are also not round when they're young. So why were they not round? Probably they weren't supposed to be round, but we didn't know that. So I've got a movie to show you that shows how galaxies might have grown. So how do you make a movie of galaxies growing? Well, you say you imagine what the universe was like when it was young. You take the random hot and cold spots that I showed you in the microwave map, and you say, okay, now I think I know what the laws of nature are, and if all that's true, then I could be able to simulate it in a computer and make a movie. So here I'm going to show you a movie of 13.8 billion years passing before your very eyes in about a minute. And if this works, then you'll see galaxies growing very quickly and in a very stringy way. There they are, they're just beginning to appear. The computer people have rotated a box of imaginary material in front of your eyes So you can see the three-dimensional structure beginning to appear. So right in the very first billion years, the galaxies are already stretched out in strings. And once in a while, it even looks like there are sheets of material out there. And this is all just caused by gravity operating on the random initial state of the universe. Now, after a little while, things start to explode. Why do things explode? Well, two things release immense amounts of energy. Stars can blow up. We call them supernovae. And also black holes can form, and immense amounts of energy can be released when things fall in and are compressed. So here we have the cores of galaxies are beginning to explode for both of these reasons. And it would be a dangerous time to be near those objects, eh? In fact, it's probably one of the reasons the solar system is not in the middle of our own galaxy. We are quite far from the center, and our galaxy has a big black hole in the middle also, which at one time would have been bright enough to sterilize any planet that was anywhere nearby. So this runs along for, things keep on exploding for quite a long time, billions and billions of years. And then when about 9 billion years have passed, some galaxy like ours may be forming a solar system. Solar system is about 4.5 billion years old, so about 1/3 of the age of the universe. And you see amazingly stringy structures. So we shouldn't be really too surprised when we see observations of stringy galaxies way out there in the beginning of time. So, by the way, people ask me about artificial intelligence. We're beginning to use artificial intelligence and machine learning to make this calculation cheaper and better. So some galaxy like ours is one of those sort of average little small ones out there. And imagine that there's a Milky Way galaxy with a solar system in it, sort of like ours. So what did we see? Well, here's a picture with one of those highly magnified images. This is a galaxy which is called a sparkler because it has lots of little globular clusters. So you can see a few globular clusters with your own eye in our own night sky, if you don't live in town, anyway. So now here's the question of, did those come before the galaxy, or did the galaxy make them as it grew? Here's a totally astonishing picture. We have a curve that shows that once in a while a star happens to be magnified by 10,000 times or so. So this curve, I don't have time to tell you much, but you see they've marked a thing called lensed star. So it just happens to be right where the gravitational lens has unlimited magnification. So we have learned about an individual star at immense, immense distances. Here's a picture I show you for two reasons. One because it's beautiful, and one because it tells you a story. There are 5 galaxies in here. The one on the left is pretty nearby, and it's near enough that you can see individual stars in the image. The other 4 are in the process of crashing together. And so we can now reveal the details of the crash. By the way, what happens when 2 galaxies crash together? The stars do not hit each other. Stars are small, space is large. But the gaseous material that's in between them will crash into the other gaseous material and prompt all kinds of crazy activity, including formation of new generations of stars, which is what is illustrated in those pink areas. Those are brand new stars that are just lighting up the neighborhood because of the crash. And the top galaxy has a very bright core, which is because there's a black hole in there. Here's another beautiful picture. We call it the cartwheel galaxy for pretty obvious reasons. We now say the reason it has that shape is that another galaxy went straight through the middle and pushed out all that splash of material that has now lit up and formed new stars around the ring. So this is a kind of star formation laboratory. Tells you what does it take to make a new star form in very extreme conditions after this huge crash. Here's a galaxy that has holes in it. Well, now we can say most of them do. This is a picture that's taken to reveal the presence or absence of dust. So it's made with the longer wavelength camera, And so you see those holes in the galaxy. Those holes are there because of the same reason there are holes in sponges. In a sponge that you buy in the store, the holes were made by gaseous pressure, pushing the sponge material away. We have something like that here. When stars are newly formed and they're hot and bright, they send out a lot of energy and push away the neighborhood, push away the gaseous material. So all of those holes are because a new generation of stars was recently formed a few million years ago. So that's a picture we can now begin to appreciate. When we had the previous pictures of this galaxy, it looked very ordinary, just a simple old spiral galaxy. Here is a thing we call the pillars of creation, a place where stars are being born close by, not in some other galaxy, but right here. This is a few thousand light years away from us, and you can see in this case it looks like there's a wind blowing from the upper right to the lower left, sort of ripping away the material that's already there. This is a case where the bright stars, the new stars above, are pushing the material away, and they're prompting new stars to be born inside this cloud. So once in a while in this picture you see a bright thing. I can't really aim my pointer well enough to show you, but there's on the middle right, there's a little red stringy thing that represents new stars being born. There's a few others, and you can see some very strange shapes, which eventually we'll be able to make our digital movie and say, well, this is how that star is being born in there. So here we have a picture of a new star being born. This time we're looking at the hamburger, between the hamburger buns. So right in the middle, there's a flat surface that goes right through. What we're seeing is edge on into the formation of a new solar system. So our solar system is flat. All the planets orbit in the same plane. And when it was formed young, there was an awful lot of dust orbiting around that. So what we're seeing here is that that new solar system is full of dust, and it's all opaque when you look at it edge on. There's a star right square in the middle, and if you could imagine being over there and looking down or above, you would see the bright star. That's what's lighting up the up and down parts. If you come back in a few 100,000 years, probably, most of this dust will be cleared away, and the planets will still be there if there are any, and we think there would be, because almost all stars have planets, and about 20% of stars have the planets of the right size and temperature to be like Earth, which gets us onto the question of, are there any others like home? And the answer is, we don't know, not yet. We have had a few lovely surprises. Here is something we call Jupiter mass binary objects. So we thought we knew how planets would form. They would be forming in orbit around a star, like that picture I just showed you. But here we found in the Orion Nebula, well, that's not really so either. We have objects about like Jupiter, but forming in pairs. So, well, does that mean Jupiter is really a tiny star? Just too small to light up, or what? Oh, and you should ask me, how can you see them if they're like a planet? Don't they planets shine by reflected light only? And no, not really. When they're young, they can be pretty hot. They're formed hot as they're being born. So here we're seeing them. There are several dozen of these things over in Orion Nebula. By the way, you can see the Orion Nebula yourself. It's the middle star in Orion's sword. And so if you get your binoculars out or a small telescope, you can see it's not really a single star. There are dozens of them in there. So you can't quite get this picture yourself. We really needed the Webb telescope to get it, but you can look at the same place where we took that picture. We are very interested in whether there are stars like, if there are planets like ours. Here is the method we can do with this telescope. If you wait for a while and you look at enough stars, sometimes you'll see a star will blink for a while, a few hours or a day or something. As the picture on the right is trying to show you, when the planet goes in front of the star, it blocks some of the starlight. And as it moves across the face of the star, brightness changes. If the planet is a rock, then the amount of area that it's got is independent of wavelength. If it's got clouds or an atmosphere or something, its apparent size will be different depending on what the atmosphere is like and what wavelength you're using. So here our plan is to look for stars where this happens and look at this light that goes through the atmosphere of the planet on its way to our telescope. So we know this works. We have found many planets like this. The little ones seem to have no atmosphere at all, sorry. But we were not surprised because the only stars for which this works well are called M stars, and they're very hostile. So how can a star be hostile? Well, the same way that our sun can be hostile. Once in a while, the sun sends out giant blobs of magnetized material. And the last time a big one happened, it wiped out the power grid in Quebec for a while. In 1859, we had a bigger one that was so bright that you could see, the aurora was so bright you could read a newspaper in the middle of the night. So there was such great electrical effects that you could get sparks off your telegraph keys in 1859. So if these stars are little, and they do this a lot, and the planets are very close, so the guess is, well, anybody that's unlucky enough to be there is going to have the atmosphere ripped away real fast. So it's no surprise that this didn't work for those planets. So we know what we have to do next is to build an even bigger, better telescope. So just to illustrate some more things that we were able to do here is Jupiter, as you have never seen it before. The great red spot isn't red, of course, because infrared isn't red. So we have to make up imaginary colors to show you something. Here the system usually, by the way, is short wavelengths are shown as blue, long wavelengths as red, in between yellow or green. So there's a meaning to the colors, but they're not the ones you could ever see with your eye. So Jupiter is a fascinating object. We can now watch it every day that we want to see the weather. Jupiter turns around about once every 10.5 hours. So you have to actually be quite diligent about how you make a picture of something that's spinning while you're taking the picture. So it has lots of satellites. One of them, which is completely fascinating because it has the possibility of having life. I don't have its picture here, but it's called Europa. It has ice covering an ocean, and one of these days we plan to send a probe out there to fly through the water jets that are coming out from the cracks in the ice and see if there's any sign of organic molecules in that water. Well, your guess? Well, my guess would be, yes, there'll be organic molecules. So here is another thing we did. You might know that NASA attacked an asteroid. We dropped a big block of metal on it to see what would happen. This is an asteroid which is part of a pair, and we chose it that way because we'd be able to tell very well what happened afterwards. So we took a picture with Hubble, we took a picture with the Webb, and everybody else who had equipment tried to take a picture. So knowing what happens when you attack an asteroid is pretty important because you want to know how much is it going to move. In this case, a lot of debris came out, and also the asteroid moved about 5 times as much as it would have if it were just a billion balls colliding with each other. So we're learning about how to protect you from asteroid crashes. So the big ones, it's been 65 million years since we had a big one, but it's only a few years since we had one over Russia, in Chelyabinsk, I guess it's in Russia, where a fair number of people were killed because they went looking to see this thing that came slicing through the sky, and windows were knocked out and people were killed by the glass. So do not run out of the house when one of those comes over. And similarly, when you get an earthquake, do not just suddenly run out of the house. The windows may be falling. So here is another place we're going. We are sending a probe to land on the surface of Titan. And we're taking its picture now to see what is the chemistry of the surface like. Titan is a moon of Saturn, and it's real cold out there. But nevertheless, Titan has an atmosphere, and it's the only satellite of any planet in the solar system that has much of one, and it's enough to fly a helicopter. So we have built a helicopter, we're building it, I should say, which is planning to land out there in 2034, and we'll go hopping around the surface to see what is it like. So apart from the fact that it's just interesting to try this, this is a place where nature may have tried the experiment to see, does life require the conditions that we have here, or could it exist in another place? So Titan has rain, it has clouds, it has lakes and rivers, has weather. Now it's cold out there, so it's ethane and methane out there, but they're sort of like solvents, and the surface is solid ice, water ice. So there's an experiment. It has just been done by nature to see, can you combine all those ingredients and get life? Your guess? I don't know. My guess is, well, it's probably pretty unlikely, but you should look. So we have got a nice picture of Uranus, which is the only planet in the solar system where the spin axis is almost in the plane of the solar system. So every now and then we get to look almost straight down on the pole of the planet. So there it is. You can see that planet has beautiful rings. We know from the Webb telescope that all of the planets outside, from Jupiter on out, they all have rings. Jupiter, Saturn, Uranus, and Neptune all have rings. And it's really fascinating to understand how that works. These rings are debris from things that have collided, and they tell us about how the particles collide with each other. And you say, well, is that important? Yeah, sort of, because originally particles collided with each other and they stuck together to make planets. So how did the Earth get formed? From colliding particles sticking together. So just to say that wraps up much of the story about the Webb telescope, and you find all of our pictures online. They have been very well covered by the news media, and so there are many things to tell you about that. If I have another couple of minutes, I might indulge in showing you what's coming next. We already have this satellite up that was launched by the European Space Agency on a SpaceX rocket, by the way, and it is looking for signs of dark matter and dark energy. So it's a pretty small telescope, but it's powerful enough to find out something exciting. We are building this giant telescope in South America. It's named after Vera Rubin, who was one of the astronomers working on the nature of dark matter. So there's dark matter out there. It's a great mystery to astronomers. And this telescope, named after her, will be taking a picture of the entire sky every 3 nights. And that means that they will be able to say about 10 million things changed since last time I talked to you. So we don't have enough graduate students to follow them up. We're going to be using artificial intelligence and every other computer trick you can imagine to decide what does that all mean. But things change when you look carefully. Some things explode, some things move. There'll be lots and lots of asteroids, and like it or not, there'll be lots of tracks from satellites like the Starlink. So astronomers are annoyed, but there's not a lot we can do about that. But one heck of a telescope. We are launching, NASA is launching this one, named after Nancy Grace Roman, who was the head astronomer at NASA headquarters for many years. This was supposed to go up in 2027. If you visit us at NASA in Greenbelt, Maryland, we are working on it there. You can see the pieces that we have. So this is about twice as big as that European one, and it's also looking for dark matter and dark energy signs, and will also have a camera to look for planets around other stars. Is it likely to be able to see an Earth-like planet around a star like the Sun? Probably not, but we're certainly going to try. We certainly will look. And then who knows what next? Astronomers declared that they want this telescope, the Habitable Worlds Observer. So it's about as big as the Webb telescope, only much more perfect, and it would be capable of seeing Earth orbiting another star like the Sun. And why would you want that? Well, because that's the one example that you ever have seen in the whole universe of life on a planet is like this one. We got one example, so please find more. So that's the plan, and that astronomers have said they wanted that, and as I mentioned, that's our plan, ask for another bigger, better telescope. So maybe I'll wrap up here because there's so many more things to talk about, but I'd be happy to talk with you about your questions. Thank you.
Hello. Okay, so thank you, Dr. Mather. So now we will have the Q&A, which, because people sometimes ask a lot of questions, it will maybe go for 15, 30 minutes. So if you want to leave, maybe you should give you a minute for people to leave now if you don't want to stay for the Q&A, because so we don't have people trickling out during the Q&A session. Those of you who want to ask questions, you should line up on the microphones on both sides, and we will proceed. It will take 15 minutes of questions, so. Yeah, okay, we'll get to it. 1 second. Okay. Okay, so please line up at the microphones, those of you who want to ask questions, and we'll take as many as the spirits allow. Okay, thank you. Please go ahead.
Okay, why do you have to take a month to cool it off, the Webb telescope? Why do you have to cool it down?
Let's see, I couldn't hear that well. There was some kind of sound interference. Say that again.
Okay, why did you have to take so long to cool the telescope?
Oh, why does it take so long to cool the telescope? We designed it that way. And also, another way of saying it is a metal object is not very good at emitting heat. Because we've coated it with shiny stuff. If it were made black, it would have cooled off a lot quicker.
Why did you have to cool it at all?
Oh, why do we need to cool it? So that it doesn't emit its own infrared light. So we're all transmitting infrared power. The telescope better not do that or we won't see anything. And that's why we have to put the telescope out there, because it can't be cold if it's here. So I should have told you why we'd build a telescope such a strange design. It has to be bigger than the rocket to be sensitive enough. It has to be cold. It has to unfold in outer space. And we would have done it a simpler way if we could have. There wasn't any simpler way. Okay. Okay.
How many planets that are like Earth have been found in the Milky Way yet?
How many satellites are there in the Milky Way?
How many planets?
Like
How many planets in the Milky Way? Almost every star has a planet. Almost every star has a lot of planets. So there are about 100 billion stars in the Milky Way, so maybe almost 1 trillion planets. Plenty.
Are they like us?
And are there any like us? Some probably yes. We have no way to be sure, but we think there's nothing that special about the solar system.
magical yet?
So it's a magical yes. So honestly, we need to build another telescope to find out. So by the way, people want to know why do we think life might be common elsewhere? And so we have one observation. Here it is, we have Earth, and life. There are signs of life in the fossils that we have that occur within a few 100 million years after the fossils that say there was an ocean. So a few 100 million years for an ocean to make life. That's what we have. And then all the rest of time for us to turn up. So is human life or a complex civilization like ours unusual? Clearly, yes. But who knows, really?
So the James Webb is made to view infrared, correct? What would happen if you made a telescope to view ultraviolet instead of the infrared, so the opposite end?
Okay, so his question is about what would you see with an ultraviolet telescope? The Hubble telescope does pick up ultraviolet light, and so it shows things that are pretty different. It shows things that are much hotter than the sun. To emit a lot of ultraviolet light, you need to be a lot hotter. It shows some of the major chemical signatures of special atoms like hydrogen that show up better at the ultraviolet wavelengths. If there were a planet that had ozone on it, you would see that. So ozone here makes the ultraviolet stop in our own Earth's atmosphere. So if you found a planet that had a lot of ozone, you'd say, maybe they have oxygen also. So that's a really interesting thing to try. So, and that's what the new telescope, the Habitable Worlds, would also do. Look for the ultraviolet part. Yeah.
More questions.
Oh, another question way over there?
Can you speak to some of the recent reporting that says some of the observations seem to indicate that the universe is about twice as old as we think it is?
Yeah, I've seen some of that. I just do not know what they're thinking. We have extremely good evidence for the story that we tell, and somebody has to ignore that evidence to make that other claim.
So what was the biggest upset to conventional models from before JWST? Was it this galaxy morphology? Can you say what your theory is for how we resolve the surprises?
Okay, so the question is, why didn't the galaxies, why are they different from what we thought they would be? And I think, number one, it's just really hard to extrapolate to very different conditions. So the average density of the universe was thousands or 10,000 times higher than it is now. So the way the galaxies would grow would be pretty different. The temperature was a lot higher for everything. It does seem that we just don't understand how stars grow. So it looks like the stars are bigger and brighter and hotter than we thought they would be, and they grow more efficiently than we thought they would be. And so it's probably just we don't understand how stars are formed, which is not a surprise. When I showed you the movie about how the stars are made, we had to make up a lot of that stuff because we don't know. You have to say, you make a movie about something you imagine, but then you say, well, does it match reality? And now we're getting to say, well, no, it doesn't exactly. So we have to change the movie now.
My question is about temperature. What temperature were you waiting for the satellite to get to? It probably can't get to 2.5 Kelvin from where it's at because we're so close to Earth, right? And then how far away from Earth do we have to get, or from the sun do we have to get till we get to that temperature?
So how far away can we measure temperature, for instance?
No. What temperature were you waiting for the satellite to get to?
How cold do we have to get the satellite?
And also, how far away from Earth do you have to go before you reach the temperature of the universe?
Okay, so we needed the temperature of the telescope to be about 40 or 50 degrees above absolute zero, so that it doesn't send out its own infrared light. Okay. And then if you had a perfect sunshade, so that the telescope could cool itself all the way down to the cosmic temperature, it would go down to about 3 degrees above zero, the cosmic microwave radiation that we measured from the Big Bang. So nothing will get colder than the Big Bang.
So then, so Earth is, as we leave just the atmosphere of Earth, it's around about 3 Kelvin?
Yeah, if you get really far from the solar system, the temperature is down to 3 degrees.
Okay. That's
Of course, the sun is pretty bright. You have to go really far.
Right. Okay, thank you.
Yeah. Okay, any questions on that side?
Thanks for the great talk.
Well.
So you mentioned that the colors in the photos that you showed were due to the wavelengths of the lights. Are those lights captured in the telescope itself, or is it basically modeling to make us understand the photos that it captures?
Say that again. I'm actually a little deaf, to tell the truth.
That's fine. So you mentioned that the colors in the photos that you showed are because of the wavelengths of the light. So red, blue, orange, pink, all of those colors in the lights are just different wavelengths of light that is captured in the
Yeah, so when we show you a color, we have to make up something that means something.
Okay.
Because, of course, we people cannot see any of those colors. We try to make them meaningful so that shorter wavelength is blue and the long wavelength is red. And then once in a while we do something different. Like when I showed you the pink and blue blobs in the original map of the cosmic microwaves, just we make red brighter and blue fainter because we only have one color to show. So different ways that we code that, just trying to be informative, not trying to kid you.
Okay, thank you. It's measured in the telescope. Okay, thank you.
Hi, in the intro there was some mention of a proposal you had for a hybrid space-ground telescope. I was wondering if you could say more about that.
The idea here is if you have a telescope on the ground, can you make it better by adding something in space? So a couple of wild ideas. If you could make a thing that was cast a shadow of a star onto the telescope, then you'd be able to see the planets orbiting near the star. So to do this, I need something that's 100 meters across, which is, I don't think it would even fit in the auditorium here. And it needs to be 170,000 kilometers away from Earth to do it. But why not think about it? So that's one thing. A current idea is how about making better pictures of black holes? You saw the Event Horizon Telescope made these little picture of orange rings around the black holes. They could do it a whole lot better if they could have another antenna in outer space. So we are planning to propose that. My friends that are working on it are going to propose it, and so maybe we'll get to do that. So then you could measure how black holes spin. So, you know, black holes don't just sit there. Things do fall in, and when things fall in, they can make it spin. So we'll look and see if that happens.
Thank you so much.
Hi. I was wondering what's some advice you have for young people who are interested in studying the universe?
Well, am I going to start where you are? Because everything's interesting. If you want to study science, you know, pick up the rocks and look under them because that's interesting. Somebody's living under that rock. Maybe there's sand grains in there that came from the Big Bang. There are little bits of meteoritic dust. Once in a while, tiny meteorite dust grains fall from above and they're mixed into the dirt. You would never recognize them, but they're in there. Once in a while, you get lucky and see something close up. In the meantime, if you can't do it yourself, try making a telescope with some lenses. I did that when I was a kid. Try making electronics, learn how to do that. Study the science there is to study. And if you want to be a space astronomer, you might need to know biology, because we're now getting to where space biology is important. So if you want to be a doctor, we might need you in space. If we want to send somebody to Mars, they might need a doctor there. We might need two, because what if the doctor's sick? That happened when we sent people to the South Pole, by the way. We had to rescue the doctor. So basically, anything you want to study, we need it for NASA.
Hi, question about L2 point. So I wonder why the telescope chose to go to L2 point. Is this point special?
Tell me that again.
So I wonder why the telescope chose to go to the L2 point. This point special?
Why does it go to that particular point?
Oh, why do we go to the Lagrange point?
Yes.
Thank you. We go there because it's a great place to, well, number one, it's relatively close to Earth, and number two, the sun, the Earth, and the moon are all in one direction. If you put up your umbrella, the telescope will be completely protected. So that's the reason to go there. Anybody on that side?
So I had a question about CMB telescopes. So there's been Kobe, Acme, WAMAP, Planck. Are there any plans for any additional telescopes beyond this? And if so, would they just be to map the CMB in further detail, or would there be any other observations of interest that you'd like to learn more about?
Yeah, I'm still having trouble being deaf.
So for the CMB, we've had a lot of telescopes that we've sent out to map it. So are there any future plans for new telescopes? Would they just be to map it with a higher resolution, or are there any other objectives?
So she's asking about the cosmic microwave background radiation. And we've already had 3 satellites up there to measure it really well, and we're not done. So we need another one of some sort, because it is predicted that if you could have Polaroid glasses and measure the polarization pattern of those spots that we show you, they would tell you something about the Big Bang. And in particular, they would tell you if there was something we call gravitational waves in the early universe. And maybe there were, and maybe there weren't. And it's a big question that would address the nature of matter and the nature of energy and all the kinds of things that are mysterious to physicists. So it would be really, really important. So we know what we have to do, and we don't know how hard it is. A lot of people are trying. Many satellites have been proposed that would do that, and one is actually already approved, sort of. It's not launched yet, but it's a collaboration with Japan. So soon we may have an answer. But chances are it's going to be a tricky answer, because it's so important. We're going to argue about it. That's one of the hardest things there is to measure.
Thank you.
Okay, let's try a question from over here.
Hi, I noticed that the new telescope is also designed to detect like the dark energy and dark matter. So how do we detect those things don't interact with light and those things interact with light with the same telescope?
So I'm still having trouble with the sound system. Tell me.
Yeah, I see that the new telescope is like also detect the dark energy and dark matter, which don't interact with the light. How do we detect those dark energy and dark matter?
So he's sort of asking, how do you detect dark matter and dark energy? Well, you can't see them.
Yeah.
So they're transparent. So what you do is detect their effects on the positions of things. Like the dark energy is the name we give to the fact the universe is accelerating. It's going faster and faster and faster every year. So now you need to say, well, is that a constant acceleration or is it changing with time? So that's the number one big question. So we look at, see, can we measure it as we look back in time? Was it always the same number? And it could be variable. We didn't know why it was there in the first place, so we don't know whether it's supposed to be constant or not. The question about the dark matter, how do you detect it? Well, number one, it's got gravity. So our first evidence was that objects like the Milky Way or other galaxies spin too fast. You can't explain how they can hold together unless they've got more mass pulling themselves together to hold them in. So the calculated mass of galaxies is 5, 10, 20 times as much what you can see. So something's up. We've known this since 1935 or so. And now, okay, but now let's go measure better. And still, we don't know what it is. People here are trying to measure dark matter in the laboratory. Every big university seems to have a project to measure dark matter in the laboratory. So far, the answer is very simple. Can't see it yet. But we're sure something's going on. So don't give up yet. So it could be something they call weakly interactive massive particles, which is like particle physicists study. Could be a new kind of thing called an axion, which nobody's ever seen. And it could be what astronomers can imagine. How about dark black holes? How about lots of little black holes? And so far the answer is, well, maybe.
So you can go over there. But
Okay.
So you don't have to run.
Okay.
So you don't have to run. I'll repeat the question.
Oh, okay.
So why don't you?
Okay.
So why don't you just stand here? Ask your question.
Yeah. I was curious about your opinion on the LUVOIR telescope proposal. I know it's faced a lot of criticism for being overly ambitious, too much risk for a single platform. I wonder if you agree with that or if you think it's a reasonable proposal.
Okay, so he's asking what we call the LUVOIR, the Large UV Optical Infrared Telescope. And we have now decided that's the next thing to do, but it's a little smaller. We call it the Habitable Worlds Observatory. And I showed you a chart that basically says, I don't have a picture of it yet, but it would look a lot like the Webb, only better in some way. So it's pretty ambitious. It needs to be ambitious. It would be worth being ambitious. But we have a lot of new technology that we did not have 20 or 30 years ago. When we finished the Hubble project, people said, what do we do next? Please build us an infrared telescope, because that we don't know anything practically about infrared. And so then but it was pretty clear then the next step after that was build a more perfect, larger ultraviolet visible telescope, Hubble, only bigger and better. And so we know that's what we need to do to answer many questions. I think if we build it, astronomers will be thrilled, and you will see another flood of astonishing detections, including things about planets. So keep our fingers crossed that we actually can carry that off. We need to make a design. Right now we can't even start the design because we got other things we got to finish first.
So apparently what we know about dark matter in galaxies is from, you said, observing it. And since the JWST can see like the galaxy on multiple layers and different wavelengths, what would a specific dark matter telescope be able to offer us that the JWST doesn't?
So what does a dark matter telescope do that the Webb telescope doesn't? The way we have to see the effects is how does it influence the motions of galaxies and the numbers of galaxies? So the answer is catalog practically everything you can see. Measure all the galaxies you can find and see what patterns do they tell you. And so they will tell you from that about the dark matter and the dark energy. So also see if the galaxies are all round. So that Einstein's lenses actually make distorted images. So if the galaxies are supposed to be round but they're not, it's telling you something. So there are a lot of tricky things to do, but we've got our ideas, so that it makes a very tough engineering problem. But we know what to do, sort of.
You've got the whole universe to play with.
Yeah, we've got the whole universe to play with, as he says, but we actually don't get to do an experiment. You don't get to say, I did this to the universe and it changed.
That we noticed.
Yeah.
You had mentioned the use of AI when simulating and studying. How do you guys plan to use that in the future?
So AI, how do you use AI? Number one, you look at we're going to let the AI analysis look at the pictures we get. Anything here that we didn't expect. So the way we do that now is everybody in the world can look at our pictures, anything here that you didn't expect. And so once in a while somebody says, look what I saw, and we said, thank you very much, let's go look at it some more. So there's a very famous one called, I think, Henny's Blob. And a Dutch housewife saw this. So we followed it up. It was green in the picture, and there wasn't anything else green we'd seen like that. Okay, but we need artificial intelligence to stand the zillions of pictures we're going to get, especially with that one that scans the whole sky every 3 nights. Nobody's going to possibly imagine studying that without artificial intelligence. So, okay, that one. The other thing we do is we try to use machine learning to help make our calculations quicker. So that simulation I showed you about the galaxies growing, that's really, really expensive to do in the supercomputer. So a lot of it's kind of repetitive, doing the same thing over and over and over. Can't you sort of paste things together? So maybe yes, they're doing it. Okay, on that other side?
In the Big Bang Theory, all matter was from one point and it rapidly expanded. Why is it 2.7 Kelvin everywhere unless it's by a star? So it was in the vacuum of space, not by star or planet. Why is it 2.7 Kelvin in both ways?
Yeah, your question is actually one of the most basic questions. People said, how can that part of the universe and that part of the universe all have the same temperature if everything was together a long time ago? And so part of the answer is it wasn't really in a point. The Big Bang tells you like it's a firecracker, but it isn't. But the other one is much more fundamental. So we need to know what was the early universe like, and we have invented a theory called inflation that actually gives a physical story behind it, and nobody expected it, but it gives possible explanations. So it's imaginary at the moment, but it seems to work. So when you study your math, you'll have a lot more ability to track that down. But good question. That's one of the best questions.
I wanted to say thank you for providing such detailed answers to everyone, and I'm interested to know what questions you still have regarding the universe or any overarching thoughts that you still find to be unanswered throughout your journey of being a scientist.
Questions I still have. Well, the dark matter and the dark energy, what are they? We've got decades of knowing about them, and they're still just as mysterious now as they were when we first found out. So, like I mentioned, nobody's found any dark matter in the laboratory. We don't even know if there's just one kind. There could be many kinds. The dark energy, well, maybe it's changing with time, maybe it isn't. And there's some other big mysteries of physics, which aren't so just astronomy. Why is there matter and not antimatter? So everything we know about antimatter is it's exactly the same as ordinary, except opposite. But one of them won. So that's a mystery. And so particle physics people have been working on that one for a long time. By the way, we first discovered antimatter about almost a century ago, too. Dirac made an equation that said there should be anti-electrons. And, well, people didn't know what that meant. Then we found them. So we have almost a century of complete mystery. The Big Bang, antimatter, quantum mechanics, almost a century old, and Einstein's relativity even older. Still mystery. People don't like it, even. People say that can't be right, but it seems to be right. Okay, some more questions over on this side.
Yeah, my question was, you said that having a big telescope that's like a bigger telescope is more helpful. What if you could make a lot of tiny telescopes, maybe, and you try to make them like one big telescope, but instead of having them on Earth, like all of them in space?
Yeah, your question, she says, well, can't you make a telescope out of lots of small ones? The answer is yes. And then some of them have been studied a lot. If you made one of my favorite ones would be able to make images of the surfaces of other stars. And you would have something like 2 or 3 dozen small mirrors spread out over a kilometer or something, and send all their light to a central focusing place and make an image of another star, and actually see the surface spots on another star. So that's not so impossible. An even crazier idea is to make 2 telescopes that are able to see individual planets, and then combine the light from those 2 in a way to see details of the planet. So that's really, really hard, because we can't even do the first step. But anyway, lots of ideas. And I've been hearing here at the university about ideas to use radio signals to measure the actual distances to distant objects with telescopes that are spread out across the whole solar system. So not impossible. Not impossible. And sometimes very valuable, just pretty hard. So this is actually probably a good place to wrap up.
The last question. Thank Dr. Mather again. Thank you, everyone, for coming. Please go to frontiers.uw where all the lectures, you can find them, they're all recorded. The upcoming lectures will be there. And there is someone left a red backpack in the reception room. So if that's yours, you should pick it up. But thank you very much for coming. And I look forward to seeing you again in the fall.